Hello, everyone. Welcome back. Let's continue. The third speaker in this session is Professor Pavel Kolesnikov from Sobolev Institute of Mathematics. The title of the talk is Dendriform Splitting and Chiral Algebras. Let's welcome.
Thank you very much. I am very grateful to the organizers for inviting me to submit a talk at this seminar and for this opportunity to share some recent observations about such topics as conformal and vertex algebras. More generally, I call them chiral algebras. This is also a popular terminology. The plan of my talk will be as follows. I will start from the topic of conformal algebras. Well, let me stop video just in order to make everything more smooth. But in the exposition about conformal algebras, I will start from so-called Novikov algebras. These are ordinary, in some sense, non-associative algebras, but they are closely related to Novikov algebras, and I will try to explain how they are related. And then in this first section, I will discuss some standard constructions about operatic definition of conformal algebras and how to determine different varieties of conformal algebras. The second section will be about more general structures, mostly known as vertex algebras. But vertex algebras are precise algebraic systems that appear in mathematical physics in a more general and more algebraic framework. I would prefer call them chiral algebras. So vertex algebras are particular cases of chiral algebras in this sense. I will discuss relations between vertex and conformal algebras and the well-known Poisson-Birkhoff-Witt theorem for the left adjoint functor for the forgetful functor from the category of vertex algebras to the conformal. And finally, in this second section, I will briefly discuss the operatic approach to chiral algebras, also from literature. And in the third section of my talk, I will recall so-called preLie algebras. We will meet them in the very first section, actually. Novikov algebras are in particular preLie algebras. And then we will discuss the general Dendriform splitting of identities of non-associative algebras and turn to the main subject of my talk, pre-vertex algebras, and some results about them. So let me start from the first section of my talk about conformal algebras. Actually, this story starts in 1980s. Boris Dubrovin and Sergei Novikov, in a series of papers, developed what they called Hamiltonian formalism for partial differential equations. Namely, they started from the consideration of one-dimensional partial differential equations of hydrodynamic type. The latter means hydrodynamic type is that the right-hand side of the equations, right-hand sides are linear with respect to space derivatives. The system of hydrodynamic type in very general form looks like the following one. we have unknown functions in two variables, t and x. T is time variable, x is the space variable. They are called field functions. X ranges in some domain. Then the differential equations describing some dynamical system look as follows. The time derivative of ith in the unknown function can be expressed via functions themselves with no restrictions and linearly depends on space derivative. The dot above a function stands for time derivation and prime stands for space derivation. For such a system, one may try to define what is called a generalized Poisson bracket. The classical Poisson bracket in ordinary differential equations, when we have only one variable, say t, and when we have no space derivatives here, the classical Poisson bracket has the following property. Poisson bracket of the Hamiltonian with any of the field functions gives rise the right-hand side of ith equation. In partial differential equations, Hamiltonians have to be presented as integrals. And what is more essential, Poisson bracket has to be not just a function, but a generalized function. It has to depend, first of all, it is defined for two field functions in different space variables, x and y. And the result is a generalized function that depends on the Dirac delta function and its first derivative. So this is not a function, but generalized function. In this form, we can try to define such a Poisson bracket so that the right-hand side of ith equation may be obtained as a bracket with the Hamiltonian. Well, let me state a very simple example. Suppose we have only one field function, m equals 0, and the equation looks like that. U dot is negative 3u times u prime. For such a system, for Hamiltonian, you may consider the integral of u squared by dx with the coefficient 1/2 just for convenience. If u represents a local velocity of some fluid, for example, then this integral would be total kinetic energy of the fluid over the domain omega. And as for generalized Poisson bracket, one may consider the following formula. The coefficient at the derivative of the Dirac function is 2u. And the coefficient at the Dirac function itself is u prime. Then this is a very straightforward computation, which is actually an exercise in elementary calculus, is that the Poisson bracket of h and u is exactly the right-hand side of our equation. One has to remember the main properties of the delta function. The integral of some function in x times delta is the same function, but in the point y, as well as if you multiply f with the derivative of the delta function, then the result would be negative f prime, just obtained by formal derivation from here. And the very particular case of the generalized Poisson bracket is related to the case when the generalized bracket linearly depends on field functions and their derivatives. This case gives rise to what is called Novikov algebras. They were actually introduced by Gelfand and Dorfman in 1979 in a different setting. Gelfand and Dorfman studied formal variational calculus and Hamiltonian differential operators. But in the paper by Balinsky and Novikov, the following statement was proved. Suppose we have a linear space, n-dimensional linear space with a basis given by field functions u1, un. And suppose circle is a bilinear operation on V. So this is just some bilinear. Then the space V equipped with such a bilinear operation is called Novikov algebra if the following generalized bracket is actually a Poisson bracket, that is, satisfies the Jacobi identity. It is skew-symmetric automatically, but if this bracket satisfies the Jacobi identity, then this operation circle is said to be Novikov product. And in the same paper by Balinsky and Novikov, the following identities were derived. V with the circle is Novikov algebra if and only if it satisfies the following two identities. They called left symmetry and right commutativity. As for right commutativity, everything is more or less clear. The operators of right multiplication commute. Multiplication by V and W can be interchanged. As for left symmetry, the left symmetry is very essential for us. It is also easy to describe. The associator of U, V, and W. The associator is invariant if we interchange V and U, the first two letters. V, U, W. Well, but why do we restrict only to the first derivative of the delta function? Actually, one may try to extend this distribution further to consider some coefficients with second derivative, third derivative of the delta function, and so on. In this case, we actually come to another structure appeared independently in two-dimensional conformal quantum field theory. There is a famous paper by Belavin, Polyakov, and Zamolodchikov of 1984. They introduced what is now called the operator product expansion, or OPE. An OPE is actually a formal distribution of some bracket with respect to derivatives of the formal delta function with no restriction on the number of derivatives. The only restriction is that the number of derivatives is finite. And this notion of an operator product expansion led to what is now known as conformal algebras. From now on, we will assume the base field is of characteristic 0. K is the base field. Then what is a conformal algebra? According to the original definition by Victor Katz in 1996, a conformal algebra is a linear space equipped with one linear operation. It makes L to be a module over the polynomials in the formal variable D. And then this algebra H, associative and commutative algebra, acts on the space of polynomials in n formal derivatives lambda 1, lambda n, acts from the right in the following way. The action of D from H is equal to the multiplication by the sum of all lambdas. This is the structure of K of lambda 1, lambda n as of right H module. And then we may define what is called conformal endomorphisms space, C and C from conformal and endomorphisms of L of order n. This is a space of maps from L tensor n to the tensor product of lambda space and the space L, but the tensor product is over H, assuming we have this action of H on the right. This map has to be what is called sesquilinear or 3/2 linear. That is, if you apply D to ith variable in X, then the result would be the same as X of A1, AN, but multiplied by negative lambda sub I for all I from 1 to n. This is what we call sesquilinearity. And the family of such maps actually defines an operad, a symmetric operad. So we may compose maps from we may compose conformal endomorphisms and act by symmetric group. The action of symmetric group acts as permutation of variables along with the corresponding permutation of lambdas. The definition of a composition is pretty technical, so I do not state here the details. They can be found in more recent papers by Victor Katz. In his book of 1996, he didn't use this notation, but actually in later papers, the precise definition can be found. But if we can compose conformal endomorphisms, and if we can interchange variables in conformal endomorphisms, then we may define what is commutativity or skew commutativity. We may also define associativity, Jacobi identity, and all other identities quite familiar for us, because the definition of a multilinear identity, but in characteristic 0, every identity is equivalent to a multilinear one. Every multilinear identity can be presented as a composition of conformal endomorphisms, actually. So, for example, Lie conformal algebra is nothing but a morphism of operads, a morphism from the operad Lie, governing the variety of Lie algebras, to the operad. Well, in order to be more precise, we have to get this way. To send L. Indeed, the operad of Lie algebras is generated by a single generator, the Lie product. In order to define a morphism like that, the only thing we need is to define the image of the generator. This leads us to classical definition of Lie conformal algebras, more classical definition. The image of the generator in Lie is an element from Zend L2. But every element from Zend L2 can be presented as the image of X in A and B from L. Can be expressed as a polynomial in only one variable. Say we may choose lambda sub 1, because lambda sub 2 can be expressed in terms of d and lambda sub 1. This product has to be skew linear according to the definition. It has to satisfy the skew commutativity, which is presented in this form, and it has to satisfy the Jacobi identity. So these 1, 2, 3, 4 conditions define what is called a Lie conformal algebra. Let us consider an example of such a conformal algebra. Suppose L is modulo of rank 1, and define the Lie product in this form. This product actually satisfies all these equations, and the result is known as the Virasoro conformal algebra. The matter is that the Virasoro conformal algebra can be presented by formal distributions over the Witt Lie algebra, the well-known algebra with multiplication table given by given in this form. And then, if you consider two formal distributions like that in two different variables, and compute the operator product expansion of for the product of U and in Z and U in W, then the result can be expressed in terms of the formal delta function and its derivative, its first derivative with coefficients 2U and the derivative of U. One may compare this operator product expansion formula with what we had earlier for Novikov algebras, with this one. They actually coincide. And in terms of Novikov algebras expressed later, this example corresponds to one-dimensional simple Novikov algebra, the only simple algebra over an algebraically closed field. And the Virasoro Lie conformal algebra is also the unique, exceptional, simple finite Lie conformal algebra. So this is why I have used to say that Novikov algebras are younger siblings of conformal algebras. And finally, in this section, one may note that if you replace the operad Lie here in the definition of a Lie conformal algebra with an arbitrary operad governing a variety of non-associative algebras, or even associative, say associative algebras, alternative algebras, Novikov algebras, Poisson algebras, and so on. In this way, one may get a definition of so-called var conformal algebras. Varieties of conformal algebras are obtained in this way. Originally, the varieties were introduced by Michael Reutemann in 1999. And later, I showed that this approach is equivalent to Reutemann's one. So if you go through formal distributions over ordinary algebras, or in operatic terms, the result would be exactly the same. The next section of my talk is devoted to chiral algebras. Let me state the algebraic, purely algebraic definition of a vertex algebra in a version which probably first appeared in a paper by Bakalov and V.G in 2002. According to this definition, a vertex algebra is a linear space equipped with a linear map D, a so-called translation operator, with a bilinear operation dot, which makes V to be unital left symmetric algebra, so that the map D is a derivation of this left symmetric algebra. The left symmetric means the same as in the part of Novikov algebras. Associator is left symmetric. And also, the structure of a vertex algebra presumes Lie conformal product. So every vertex algebra is in particular a Lie conformal algebra. But in the definition of Lie conformal algebra, we need also the operator D. The operator is the same as here. So this Lie product, the conformal product with this D, turns V into a Lie conformal algebra, so that the following two additional identities hold. The first one is the commutator identity. The commutator of U and V can be expressed in terms of Lie bracket, Lie conformal bracket. Here we have some integration. This integration has to be understood formally. U lambda V is a polynomial in lambda. One has to integrate this polynomial formally and compute the definite integration by the Newton-Leibniz formula from 0 to negative D, replacing lambda with the operator negative D. So this strange formula actually is just a shortcut, actually. And the second one is the so-called V.G formula. In some sense, the V.G formula is very similar to Leibniz rule. The bracket of U with the product of V and W can be presented as it is done in the Leibniz rule, but with an additional summand. The additional summand depends only on the Lie conformal brackets. This strange formula, which actually generalizes the Poisson algebra, is sufficient for the space V with these structures to be a vertex algebra. The simplest, and I would even say trivial example of a vertex algebra in this sense is the commutative associative and commutative algebra with a derivation equipped with identically zero conformal Lie bracket. This structure actually satisfies all conditions above. A more more non-trivial, less trivial example can be obtained in this way. Every vertex algebra, just by definition, is in particular a Lie conformal algebra. So we may consider a forgetful functor from the category of vertex algebras to the category of Lie conformal algebras. Just forget about the identity and forget about the left symmetric product. The identity is called vacuum vector in physics. In this way, we obtain a forgetful functor from the category of vertex algebras to Lie conformal. This functor has left adjoint one. For every Lie conformal algebra, one may construct its universal enveloping vertex algebra in the very natural sense, just like every Lie algebra has its universal enveloping associative algebra. For example, for an abelian Lie conformal algebra with identically zero product, the universal enveloping vertex algebra is just the differential symmetric algebra of the space L. So we have to consider L as a linear space, consider its symmetric algebra, and then expand the operator D into derivation of this symmetric algebra. For the Virasoro conformal algebra, the universal enveloping algebra is actually isomorphic to the same symmetric algebra of the space L, but just as linear spaces, they are isomorphic. The product in the universal vertex envelope is different. For example, let us consider the left justified brackets v dot v dot v. Using the commutativity identity, you may present it in this form. Then apply skew symmetry to change this one to this one. And then note that the weak formula applied to this product give us something like that. In general, it seems like the product of v dot v and then dot v, this one, is expressed as this one plus some terms of smaller degree. This term is of degree 3, but all other terms here, they are of smaller degree, 2 and 1. It is somehow similar to what we have in the ordinary universal associative envelope. I have also stated 2 more examples here, because the classical examples of vertex algebras like Heisenberg algebra or Weil vertex algebra, they are all obtained as some quotients of the universal envelope. But this observation is just a particular case of the general theorem noted by Michael Reutemann. For every Lie conformal algebra, the universal enveloping vertex algebra of L carries some natural filtration, and the associate graded algebra of this filtered algebra is isomorphic to the associative and commutative differential algebra freely generated by the space L. So, in obvious sense, this statement is very similar to the classical Poincaré-Birkhoff-Witt theorem for Lie algebras. However, the theory of vertex algebras may be expressed in a more categorical language. Actually, one may try to define the vertex algebra to be also a morphism from the operad Lie to some more general operad, which is somehow similar to the operad of conformal endomorphisms, but with more complicated structure. This more complicated operad I denoted in the following way: chiral endomorphisms. So CH from chiral endomorphisms. In the paper by Bakalov, De Sole, Helwani, and Victor Katz, the same operad is denoted by PCHV, the same stuff. So probably P comes from polylinear, CH from chiral, and V is the module we start with. This one. Let me briefly observe what is the structure of this operad. What are the analogues of multilinear maps for vertex algebras? In order to define this operad CHN, we have to consider some additional objects. First, let us consider the following algebra. Subalgebra in the field of rational functions in n variables, z1, zn, generated by all differences, z sub y minus z sub g, and their inverses. This Laurent polynomial algebra is denoted On. And also, let us define some differential operators of particular form. Consider the operators of multiplication by zi minus zj and formal derivations with respect to zi. This algebra Dn is an associative, but not commutative, of course, algebra. This is a subalgebra of the nth Weyl algebra, the algebra of differential operators with polynomial coefficients. But the polynomial coefficients depend only on the differences, zy minus zj. This is a well-known fact that On is actually a cyclic module over Dn, generated by a single element like that. It holds for every n. And then the space of chiral endomorphisms of V of degree n consists of all maps from nth power of V and the space On, this one, consider it as a Dn module. This space can be naturally considered as a D module, and the right-hand side can also be considered as a D module. The condition that such a map is D-linear, this condition actually generalizes this SQ linearity for conformal algebras. So actually, in the operad of chiral endomorphisms, we have the same target space, but the source space is made more complicated. We add one more argument here, an argument from the space ON. Since the module ON is cyclic, every element X from chiral endomorphisms is completely defined by its value at the generator of ON over D. And in particular, if we consider the binary case, the most interesting for us, if X belongs to G and V2, then the image in two arguments U and V from V. So again, we have can be presented as a polynomial only in one variable. Formally speaking, we have to get two variables, but again, remember that lambda 2 and lambda 1, they are not completely independent. So we may leave only lambda 1. An arbitrary polynomial can be written in this form. And in order to express this polynomial in terms of vertex operations, we have to identify the free term with number -1 with the dot product, and the remaining stuff. This is a polynomial with no free term. It can be presented as a formal integration of some polynomial in lambda from 0 to lambda 1. And the subintegral function is nothing but the conformal lambda product in the vertex algebra. So, in fact, every map from X, every map X from chiral endomorphisms V2 can be considered as an image of a generator of Lie operad. And if such a map is actually a morphism of operads, so this X satisfies some kind of skew symmetry and Jacobi identity, then the space V, equipped with operations dot and conformal brackets, as it is done here, satisfies almost all conditions about vertex algebras. Namely, the algebra V with respect to dot is a differential left symmetric algebra. The same space V with lambda bracket is a Lie conformal algebra, and the commutativity and Wick identities hold for this V. So the only thing is that we don't have vacuum. We forget about unitality. Vertex algebras without the vacuum vector, they are naturally to call Lie chiral algebras. So Lie chiral algebras are vertex algebras without vacuum. And the forgetful functor we already discussed, which turns every Lie chiral algebra to Lie conformal algebra, can be easily described as follows. Suppose we have a Lie chiral algebra, which is a morphism from Lie to the operad of chiral endomorphisms. Then Consider the following map, which turns chiral endomorphism into conformal endomorphism in the following way. The chiral endomorphism X with the last argument from On, this last argument from On. Just replace this argument with identity. Identity is an element from On, that's okay. So what we obtain would be exactly the forgetful functor, which turns a Lie chiral algebra into Lie conformal algebra. But we have no abstractions to replace the operad Lie here with an arbitrary operad of associative or non-associative algebras, say associative, alternative, and so on. And what I'm going to say in the last section of my talk is the replacement of Lie with left symmetric algebras. And in order to describe this replacement, we will need what is called the Dendriform splitting. Let me briefly recall the left symmetric identity. The left symmetric identity can be also written in this form. Just move something from right to left, something from left to right, and express it in this form. In this form, this identity is known as preLie identity. Such algebras appeared in 60s independently in the works by Cajul, Winberg, and Gerstenhaber in very different frameworks, actually. Also, Jean-Louis Lodey in 2001 introduced what he called Dendriform algebras, linear spaces with two bilinear operations satisfying some identities like that. The identities are chosen in such a way that the product, somehow commutator product of x and y, relative with respect to these two operations, is left symmetric. So Dendriform algebras are somehow associative envelopes of left symmetric algebras. Also, if you add an additional identity to Dendriform algebras like that, some kind of commutativity, then the result would be the variety of Zinn-Biel algebras. Zinn-Biel algebras are algebras with one operation satisfying an identity like that. Only one operation, but this is because this operation is the right multiplication, but left multiplication can be expressed in terms of right multiplication. The term Zinn-Biel actually comes from the Cajul duality between these variety and Leibniz algebras. So they are Cajul dual to Leibniz, and Zinn-Biel is nothing but Leibniz spelled backward, in backward order. So we obtain some natural correspondence between varieties. Lie algebras turn into pre-Lie or left symmetric algebras. Associative algebras correspond to Dendriform algebras, and commutative algebras turn into Zinn-Biel algebras. This is actually, these are three particular cases of very general construction, which was described in the paper by Babel, Guo, and me. Overall, we have to say about so-called Manin-Black product of operads. For every operad var like that, we may construct pre-var like that, just by taking the Manin-Black product with the operad of left symmetric algebras. The computation of Manin-Black product is actually a very simple task. I have prepared some slides here about that. Unfortunately, it seems like I run out of time. But in general, in order to compute the defining identities or defining relations of the operad pre-var, the only thing we need is to distribute brackets and collect similar terms. So computing pre-var algebras is a straightforward and very simple stuff. In particular, every multilinear identity defining the variety var splits into several identities of pre-var. If the degree of the identity was n, then it splits into n defining identities. They can be dependent, not necessarily independent. So preLie algebras coincide with left symmetric, pre-associative algebras coincide with Dendriform, and pre-commutative algebras coincide with Zimbelli algebras. But the matter is that the same splitting procedure can also be applied to conformal algebras. And then pre-Lie conformal algebras would turn into left symmetric conformal algebras, studied by Honk and Lee in 2015. Pre-associative conformal algebras, they coincide with Dendriform conformal algebras, studied by Honk and Bai and also Lamé Yuan. Most of the many properties of these left symmetric and Dendriform conformal algebras come from the very definition of the splitting. But we can also apply the splitting procedure to vertex algebras. Consider it as Lie-chiral algebras. Because the Lie-chiral algebra is actually defined by bilinear left symmetric operations with a derivation and conformal bracket. All things that are red underlined here, left symmetry, derivations, skew linearity, skew commutativity, Jacobi, commutator identity, and weak identity, these are all identities in some sense. Every identity can be split in the Dendriform method. This is what we can apply to Lie-chiral algebras or to vertex algebras, to apply what we call pre-vertex algebra. These are exactly left symmetric chiral algebras. As a result of application the splitting procedure to vertex algebras, we obtain the following structure. A linear space equipped with linear operator D. This is a unary operator, it doesn't split. Two bilinear operations, left and right products. These are split dot product in the vertex algebra. And also only one conformal lambda product. Only one because we have skew commutativity. The skew commutativity expresses one product from another. So we only need one. The space V with left and right product is what is known as quadri-Lie algebra. It's pre-left symmetric or pre-Lie algebra with a derivation. The conformal bracket is left symmetric conformal algebra, and the following identities hold. The split commutator identity, and three identities corresponding to the split weak identity. This is not the simplest form, but this is exactly what we obtain from the weak formula by means of the splitting. These three relations can be simplified modulo the split commutativity. Well, but this is just a definition. Do we have any examples or properties of this system? First of all, it follows directly from the definition that every left symmetric chiral algebra gives rise to a vertex algebra or Lie chiral algebra by means of the commutator. In this framework, the commutator defines a system like that. The dot product and lambda bracket can be expressed in this way. And any non-trivial examples? What we can do right now is to consider left symmetric conformal algebras of rank 1, generated by one element. And for these particular examples of left symmetric algebras, with my graduate student Ilya Dudin, we can prove an analog of the Poincare-Birkhoff-Witt theorem. We can construct universal enveloping pre-vertex algebras for such left symmetric conformal algebras, and prove that the associate graded is isomorphic to the symbiotic algebra generated by the same space. So for this particular, at least for these particular cases, we have the same Poincare-Birkhoff-Witt theorem as for Lie chiral algebras. It remains an open problem if it works for an arbitrary left symmetric conformal algebras, but this is a work in progress. So here I would like to stop. Thank you very much for your attention.
Okay, thank you very much, Paul. So very nice talk. Are there any questions or comments? So Paul, so in general, for this splitting of algebras, so one can use Rota-Bucks operator to give such a splitting. So
yes, this is a very good remark because in order to construct pre-vertex algebra, we may try to consider vertex algebra and Rota-Bucks operator on V.
Yeah.
And then exactly we have pre-vertex. It works. But
Okay.
there is a problem. I do not know any examples of non-trivial Rota-Bucks operators on non-trivial vertex algebras. The problem is that vertex algebras, even the simplest one like Heisenberg or Virasoro, they are very big. And I do not know any non-trivial examples of Rota-Bucks here.
Okay. Yeah. So at the end of your talk, you started the universal enveloping of a left symmetric conformal algebra. So could I have a look at the slides? So
This one.
yeah, maybe about here the definition. So what is the algebraic structure on this universal enveloping algebra? I mean, it's
Uh,
not hopeful algebra, right? So it's what kind of algebraic structure you can say about it?
In this setting, I mean, for the functor which turns left symmetric chiral to vertex algebras, we do not know if the left adjoint functor exists. Moreover, I have doubt, I'm not sure it exists at all. But this
Mhm.
U of L is pre-vertex algebra. What about Hopf algebra structure? I haven't thought about it. If vertex envelope can be considered as a kind of Hopf algebra. I have to look at the literature, actually. It might be known by Bayalian and her co-authors.
Yeah. So yeah, because I'm not quite familiar with vertex algebra, but in the case of Lie algebra, for example, we can show that the universal enveloping algebra of a preLie algebra, it is a pre-Hopf algebra. So there are very good axioms that those products can satisfy. There's a terminology or a notion called pre-Hopf algebra, which is namely the basic example is the universal enveloping of a preLie algebra is a pre-Hopf algebra. Yeah.
Uh, yes, indeed. This is an interesting question, even
Mhm.
for these rank one cases, because I can prove that universal enveloping exists only for rank one cases.
Ah,
But it might happen that even these examples carry some Hopf algebra structure. It
yeah,
has to be checked.
yeah. Or we can say Hopf-like structures. Yeah.
Hopf like,
Uh,
yes, of course.
yeah. Okay. Yeah. Very interesting. Okay. Are there any other questions? Uh, so or if no other questions, like thank our again. Thank you very much.
Thank you.
So, in the sequel, it's coffee time. I think we have to prepare our own coffee, right, Robert?
Yes.
Okay, okay. So let's have a break. So see you. Mhm.